All right, let's review. Before we go into chemical reactions, let's talk about how we count protons, neutrons, and electrons. And so, when we look at an element from the periodic table, we know that atoms are neutral. They have no charge, which means that they have the same number of protons and the same number of electrons. The only difference is that we can have between two of the same atom is that they may have different numbers of neutrons, which may make them weigh just slightly different. Now, when we talk about chemical reactions, the kinds of changes that we can have in the atom and where the atom actually reacts is in the area of the electrons. We're going to find that there's a possibility of gaining an electron, of losing an electron, or of sharing of electrons. Each will lead to a different kind of bond. Atoms are changed only when two of them come together and interact together. And when they react, there is going to be a manipulation of the electrons in some way. And because of those manipulations of the electrons, they are going to be held together, or we talk about bonded together. What we do not do in a chemical reaction is we never change the number of protons and or the number of neutrons. That always stays the same. Now remember, radioactive decay has the possibility of changing the number of protons and the number of neutrons as a possibility. And so as the nucleus is unstable, it's going to give off something. Of the three main radioactivities, alpha, beta, and gamma, two of them will give off a particle. In terms of an alpha particle, it's going to give off protons and neutrons, so I'm going to lose mass and I will change the number of protons that are left, which actually changes the element. In a beta decay, what we're going to lose is an electron from the nucleus and from a neutron. So I'll lose a neutron, but what that will be converted to is in a proton, and so I'll change the protons, change the element, but what I will not do is change the mass. In a gamma emission, I will become more stable in the nucleus, but I will not lose protons, I will not lose neutrons, and I will not lose mass. So there's a possibility of manipulation of or changes in the nucleus only in radioactive decay. Chemical reactions will be changes in electrons. Now I'm going to talk about two possible atoms coming together and reacting. Now what's going to happen is atom A and atom B will both put in at least one electron and interact with each other. Now one electron and another electron will pair between, and then what happens is both atoms, and I'm showing the electrons as dots, both atoms try to attract these electrons. And so they're both attracting. Another way to think about it is both are holding on to the electrons, and they're holding on, but in this case, neither one is strong enough to take the electron away. But because B is holding on to one side and A is holding on to one side, they are bound together. In terms of the extreme is when A throws an electron in and B throws an electron in, and what happens is one of the atoms attracts the electron so strongly that an electron will be taken and gained in one of the atoms. Now I'll have an extra electron. Remember, I didn't change the number of protons, so I'll become negatively charged. On the other hand, the other atom will have the same number of protons it started with, but one or more less electrons, and it will become positive. These are the two extremes. The top one is called a covalent bond. The bottom is called an ionic bond. The atoms share electrons in a covalent, And in the ionic, an atom gains an electron, and one of the atoms will lose an electron. And so I have a positive and a negative, and remember, opposites attract. Now, I'll represent a bond for covalent most of the time with a line. Each line represents 2 electrons, and they're being shared. A lot of times I will represent a ionic bond as A is next to B, and so they are combined. Now, covalent bonds occur, and I can predict whether a covalent bond will occur when I look at the atoms that are interacting. Non-metals, so 2 nonmetals reacting, is a covalent bond. A ionic bond happens when a metal, normally, and a nonmetal react. The metal and the nonmetal, one of them attracts electrons so much that it will steal the electron from the other, and creating an ionic bond. Now, these are the 2 extremes. Most of the time, or a lot of the time, when we have reactions, one is stronger than the other, but not enough to completely take it away from the other. And so a lot of times we describe the 2 extremes, the 2 kinds of bonding, but many times bonding is somewhere in between. Now, the 2 atoms are held together, okay, in a chemical bond, and in ionic, what happens is one atom will become positive, one atom will become negative, and they attract, just like we said opposites attract. But the official terminology we look is electrostatic. Electro coming from charges moving around, and static like static clean. Another way to think about it is like a magnet. The North Pole and the South Pole will snap together, and that bond is strong. Covalent bonds are shared electrons between the 2 atoms, and since both of them are holding on to something common and they don't let go, they are bound together. Now, when I look at ionic bonds and ionic compounds, there's a term that we use called ion, which means an atom with charge. And we know the atom has charge because there's an imbalance in the number of protons and the number of electrons. Now, when an atom loses an electron, it has more protons than electrons, and it becomes positive overall. It's called a cation. When an atom gains an electron, it'll have more negatives, more electrons than protons. As it started, it will become negative, and it's called an anion. And we must have, in a reaction, one atom that gives an electron and one atom that accepts an electron, so that we have 2 different charges and they will bond together. And they are bonded together because opposites attract. Now, how in the world do we predict or come up with why an atom would gain 1 electron or 2 electrons or lose 3 electrons? There is a reason why we would do that. And it is because we are looking at trying to react and come up with a perfect number of electrons that live around the nucleus. Now, that perfect number really represents a distribution, an ordered distribution of electrons around the nucleus. We won't go into exactly what that distribution is, but I will tell you there are atoms on the periodic table that represent these perfect number of electrons in a perfect shape, and they are denoted by the noble gases. In fact, if you think back in terms of how we describe noble gases, they are unreactive, meaning that they don't want to gain electrons, they don't want to lose electrons. The reason is they are perfectly balanced. And when atoms react to become ions, They react in such a way that they want to become the perfect distribution, meaning one of the numbers of electrons that are represented by one of the noble gases. Now, if we take a look at examples of trying to predict an ion, we can take a look at the element versus the ion. And so the first one I'm going to take a look at is nitrogen. Now nitrogen, when I look at the elemental form, I've given you what it looks like. And nitrogen weighs 14, has 7 atomic number. So that means, if we remember, that means we have 7 protons, 7 positive things. Since it's the element, it has no charge, so it has to have the same number of electrons. And we can calculate the number of neutrons by subtracting the mass by the number of protons to get the number of neutrons. And so we have 7. That is something that we've done before. Now remember, when I react chemically and when I create an ion, I am reacting chemically. What doesn't change is the protons. What doesn't change is the neutrons. I cannot change that in a chemical reaction. So when I look at the nitrogen, it is number 7. It can either go to 10 neon or it could go to 2 helium. Now to get to helium, it would have to lose 1, 2, 3, 4, 5 electrons to get to the number of electrons helium has. On the other hand, it could gain 1, 2, 3 electrons to have the same number as neon. Which is easier? Well, chemical reactions go to the easiest path. And so what we're going to do is we're going to 10. Adding 3 is so much easier than losing 5. So I'm going to end up with 10. 10 negatives, 7 positives. When I add up all the positives and all the negatives, I end up with a minus 3. You could write 3 minus. That's okay. If I take a look at the element sodium, the element itself, 11 protons. It is neutral, so that means it has to have 11 electrons, and it has 12 neutrons. When it reacts chemically, I do not change the protons, I do not change the neutrons, but I do change the electrons. If I look now at sodium, sodium is 11. I could go all the way up to argon, number 18, or I could go to neon 10. I would have to gain 7 to become like the number represented by argon, and I only have to lose 1 to get to the number that looks like neon. And going to 10 is much easier. So I will become, when it reacts, I will have 10 negatives and 11 positives. And so when sodium reacts and becomes an ion, it will have a +1 charge or a 1+ charge. You can write that too. If I take a look at the next element as an example, I can take a look at chlorine. Chlorine has 17 protons in the elemental form, not reacted, no charge, 17 electrons, and 18 neutrons. I do not change the protons, I do not change the neutrons. I have positive. And if you take a look at the periodic table again, if I take a look at chlorine, I could go to argon 18 or I could go to neon 10. Obviously, going to argon 18, I would only need to add 1 electron. And so the perfect number it goes to is 18 negatives, 17 positives. The total is a -1, or I could put a 1 minus. That is fine too. The element magnesium, when it's in the elemental form before it's reacted, has 12 protons, has 12 electrons, has 12 neutrons. When it reacts, protons do not change, neutrons do not change, but the electrons will change. If I take a look at magnesium, magnesium has 12. The two options are going up to 18 argon or going to 10. That's represented by neon. 10 seems much easier, and it does. becomes 10 electrons. 12 positives, if you add 12 pluses and 10 negatives together, you will get a plus 2. You can write 2 plus also, and that's fine. Now, we can look at each one individually, but I want to show you something. We can look at these individually, but I want to show you something. Look at fluorine. It has 9 electrons. When it reacts, the easiest way for it to react and become an ion is to get to the number 10, or to get 10 electrons. If it gets 10 electrons, it has 1 extra electron, becomes minus 1. We just determined chlorine will gain 1 electron to become a minus 1. Bromine, on the other hand, has 35 electrons. It wants 36 in the perfect number. That means it has 1 extra electron. It's minus 1, and all of these are minus 1. If I take a look at oxygen, starts with 8 electrons, really wants 10. To do that, I have to gain 2 negatives, 2 electrons. It becomes a minus 2. Sulfur, going from 16 to 18, has to gain 2 negatives, become a minus 2. All of these have to become minus 2. We talked about nitrogen already. Nitrogen, if it gains 3, it looks like neon. And if it gains 3 electrons, it's minus 3, minus 3, minus 3. Every family reacts the same. We looked at sodium before. Sodium with 11 wants to go to 10. It will lose a negative charge. It means it has more positives. It will be positive 1. Lithium wants to go to number 2. It will lose an electron. It will have 3 protons and only 2 electrons. It will be a plus 1. All of the alkali metals are a plus 1. We just calculate magnesium to be a plus 2. Well, calcium, that has 20, it will lose 2 to become the perfect number 18, as represented by argon, and so it will be a plus 2. All of the alkaline earth metals become plus 2. Boron, well, let's do aluminum. Aluminum is 13. Aluminum reacts, and it becomes the perfect number 10, which is the closest. It has to lose 3 electrons, becomes a plus 3. Boron will go to 2 electrons, so it will become a plus 3 by losing 3 electrons. If we take a look, there are several areas on the periodic table where I absolutely know what it's going to react. Now, let's take a look at carbon. Carbon's interesting. Carbon could gain 4 and become neon. Carbon could lose 4 and look like helium. So which one does it do? Is there any advantage to gaining or losing? Well, remember back, there are 2 kinds of bonding. Carbon tends to be one that is not weak enough to lose but not strong enough to gain, and so carbon tends to be in the classification where bonding is sharing electrons, not becoming ions to make bonds. And so we know some of these can, and we don't have to learn individual ones. We know families. Minus 1 for the halogens, minus 2 for the oxygen, minus 3 for the nitrogen, plus 1 for the alkali metals, plus 2 for the alkaline earth metals, plus 3 for the boron group. Now there's a whole big segment here right in the middle, and remember these were transition metals. I told you transition metals do not behave. This includes the anthenide and lanthanide series. We're going to see how they behave a little bit later, and they're not as predictable as we would like. And we need to remember noble gases do not react, and so we will not predict that they will react, become charged. They will not do ionic, nor will they do covalent bonds in normal situations.